Hello and welcome to this video. You've probably already heard about the latest news concerning nuclear fusion and how some people propagate this to be a way out of the energy crisis. But is this really true, and how does nuclear fusion actually work? Why do we need fusion? Why don't we simply keep our old-fashioned conventional nuclear power plants? Why do we need something new? This is what I will talk about in this video today. So maybe let's start with what happened a few weeks ago in late December and early January of 2023. Many news agencies, also the BBC, posted some or groundbreaking news about a breakthrough in nuclear fusion. So there apparently has been achieved something which hasn't been achieved before, and the topic today will be what this actually was. So maybe let's start with the problem with conventional nuclear power. So we do have nuclear power plants, we have nuclear energy already, so why do we need something new? Of course, we have to get away from our fossil fuels, we have to go to green energy, and what is the problem with conventional nuclear power? So as we know, conventional nuclear power works by splitting heavy atomic cores, for example uranium or plutonium, and getting out of one heavy core two lighter cores, and some energy will be released as well. And the problem with that is, as many people know, that heavy elements are mostly highly radioactive. So uranium and plutonium are highly radioactive, as you might know. And then there occurs the problem of nuclear waste and the permanent disposal of this nuclear waste. So and as we know, we have Fukushima and Chernobyl and so on. So all these incidents and accidents that happened with nuclear power plants when they exploded, there was a high nuclear contamination of the plants. So there were many, for example, mushrooms which were contaminated with radioactivity, and there was also radioactive rain on this land or in the surrounding where the incident happened. And many people got cancer from this as well, so there's a high problem with radioactivity, obviously. But why don't we just use non-radioactive elements? So why don't we just split maybe hydrogen or helium or maybe carbon? So why are we so intent on using heavy elements for our nuclear power plants? Well, there is actually a reason. Obviously, otherwise we wouldn't do it. And in order to get you a little bit closer to the reason why we use heavy elements, let's talk about fusion and fission. So obviously what we do in our nuclear power plants up until today is nuclear fission. So we take a heavy element, we take a large nuclear core, and we split it up into two lighter cores, and this releases energy. But what we also know is what the sun does. The sun, for example, or stars in general, suns and stars do nuclear fusion, which means they take two light elements, for example hydrogen, and fuse them to make one bigger element, for example helium. And apparently both processes release energy. And how could this be? So we have conservation of energy. We know that energy can neither be destroyed nor created. So why can both processes, fusion and fission, which are somehow reversed to each other, how can both processes release energy? That doesn't make sense. And that is the problem of today. And if we know that, we can explain why we can't use light cores in order to make our nuclear power plants work. And so in order to understand that, why this actually doesn't violate conservation of energy, we have to look at a quite famous diagram which shows the average binding energy per nucleon in mega electron volts of several elements. So for example, we can see helium here, and we can see carbon over there, we can see iron here, and maybe uranium over there. So it's just the elements of the periodic table with the average binding energy per nucleon. So a nucleon is basically a part of the atomic core. So a proton and a neutron, they are nucleons. And as we can see, due to the different atomic configurations, the different elements have different average binding energies per nucleon. So, for example, if we have a look at helium and carbon, carbon has a lower average binding energy per nucleon than helium. So theoretically, if we fuse helium atoms somehow, let's just imagine that works, if we somehow fuse helium atoms to get carbon, then the atom which comes out of the process has less energy than the two atoms which have been put into the process. So there has to be some energy which has been released during the process, otherwise conservation of energy is violated. So if we go from helium to carbon, this diagram goes downhill, so that's why we gain energy if we fuse helium atoms. Or maybe an even more obvious example is if we use hydrogen, which should be somewhere over there, and fuse hydrogen atoms to get helium, which is over there. So that's the thing the sun does in its current state. It fuses hydrogen atoms to helium atoms and some other products as well, but that's not necessary to know here. So on the left side of the diagram, so on the left of iron, so in this blue area here, what we have is an area where nuclear fusion releases energy. If we want to make nuclear fission, for example, with carbon. So if we wanted to split a carbon atom up to get some lighter atoms, we would have to put energy into the process. So in this case, conservation of energy is not violated. And the same goes for the right side of the diagram, so over here. So if we, for example, take uranium, which is used in our nuclear power plants nowadays, and fuse and split uranium to some lighter elements, so we go downhill, then energy is released. The other way around, if we would take, or if we were about to take a light element, and if we tried to fuse two of these light elements to uranium, then we would have to put energy into the process because the diagram is going uphill. And this is why there is no contradiction at all, because some elements can be used in order to gain energy by nuclear fission. So these are the elements on the right side of iron, and there are also some elements on the left side of iron which can be used in order to gain energy through nuclear fusion. And this is why we cannot use light elements in our nuclear power plants, because these power plants work by nuclear fission, so we are splitting atoms in these plants, and if we want to gain energy by splitting atoms, we have to use these unfortunately radioactive elements, which are heavy elements, and if we split them we gain energy because it's going downhill. If we take the light elements and split them, well, we have to put energy into the process, so we are going uphill. This is why we can't simply use hydrogen or helium for our power plants, because that obviously wouldn't work according to this famous diagram about the average binding energy per nucleon in mega electron volts. So, to put it in a nutshell, that means that nuclear fission can release energy when using light elements, and fusion and nuclear fission can release energy when using heavy elements. So that's the gist of this diagram. We can't use every element to gain energy by every possible process. So we have to be aware which process works with which element. Right, and this is why we are looking for a way to gain energy out of nuclear fusion, because theoretically and technically it's possible, obviously, because the sun does it, for example, but we haven't technically realized it up until a few weeks ago, because that is what has been achieved in the United States. It was the first time that we had a technical realization of nuclear fusion processes which released more energy than they needed in order to work. So we already had managed to get some nuclear fusion going in the past, but the problem always has been that we had to put more energy into the process and we got out of it. So it wasn't really an achievement, because in the end we lost energy. And the first time this didn't happen was in December in the US, at least according to the US itself. And this is partly being propagated as the end of the energy crisis. So of course the US wants to maybe glorify what they did, and they want to appear good when it comes to science. So they obviously say it's the end of the energy crisis and maybe a big breakthrough. And admittedly, it has been a big breakthrough, but not really according or concerning the energy crisis. It has been a breakthrough concerning maybe physics and how we can do things in physics and what we know about fusion. So that was great, of course, but I don't think that this has solved the energy crisis yet, unfortunately. Why do I think so? So is the hype really justified? So in order to be able to assess that, let's maybe have a closer look at the energetic balance of this whole process. So we have many lasers which transfer much energy to a gold cylinder, and this cylinder contains some isotopes of hydrogen, so deuterium and tritium, and these isotopes are being heated up to several million degrees Celsius, and normally these temperatures can only be found in like very crazy and extreme things like stars or thermonuclear weapons and like atomic bombs and so on. So you need very extreme things in order to get these temperatures going, and these temperatures are then the cause for nuclear fusion. So if it is getting like warm enough or hot enough, maybe to say it like that, fusion happens, and plop, the whole process releases 3.15 megajoules of energy. So we have 1.1 megajoule more than we put into it. So that's a total gain of 50% roughly of energy. So we should be like, oh yay, we gain some energy. We have realized a fusion process which gave more energy out than we put into it. But really, I think we forgot something. So this is of course nice, but there are some boundary conditions which we have to consider, obviously, and if we consider them, the whole process doesn't look so great anymore, because these lasers require more than 300 megajoules to work in the first place, which of course totally eradicates all the energy which has been gained throughout the whole process. And unfortunately, it's not really reproducible yet, with an emphasis on yet. So the research is still going, and our goal is obviously to make this reproducible, but it's not reproducible yet, unfortunately, but we're on a good way, to put it maybe like that. And to go on, tritium is extremely rare and thus expensive, so it's quite difficult to get this material which we need in order to make our fusion plant work. And the fusion process would have to be maintained for many hours, not only for a few seconds, which is what has been achieved in the US lately. But still, it's somehow a great achievement, and we shouldn't talk about it as if it was nothing, of course. But there's one problem which I see, and this is the greenwashing of nuclear weapons, because what the US did, or what this institute did, is they actually conducted research on nuclear weapons for the US, and they didn't really conduct research on fusion and fusion energy and saving the energy crisis. But because this doesn't make a good impression, obviously, they told the people that it's about solving the energy crisis, and that's quite creative, but yeah. So in the end, we could argue if the end justifies the means, and in the end they achieved something great concerning the energy crisis, but still we shouldn't glorify the US too much, I think, because their main intention has not been to solve the energetic crisis, but rather to invent some new nuclear weapons, probably. Right, but still, it's a proof of concept, not more and not less, which means for now it doesn't bring us many advantages, because this won't change anything in our everyday life concerning energy at all, probably, for now. So emphasis is on for now. But still, it's a proof of concept, so it is technically possible to realize a fusion process which releases more energy than it needs in order to work. And this is something very great and intriguing and groundbreaking in nuclear physics. So we should not talk about that as if it was nothing, as I've already said before. So it's a beautiful result anyway, even though there has been some greenwashing, and even though there has been some maybe glossing over the figures and so on. And even though it for now won't really change anything in our everyday life, because it's still not really reproducible and it can't give us energy in the amount we needed in order to support or supply a whole people. But still, it's a great achievement for all scientists who have been involved, and it's a great step for science. It's for now a small step for humanity, but a great step for science, because this is something which, in this form at least, hasn't been achieved in the past ever before. So, yeah, thanks for listening. If you have any questions about this topic, ask me in the comments. If you have any suggestions for upcoming videos about topics you would like to hear something about, ask me in the comments. You can see my playlist about physics here. You can subscribe me here if you want. You can see my playlist about maths here. and you can see some randomly generated video over there. I wish you a very nice day, see you soon, and thanks for watching.